here's an example of an early study that was done that was, I think, very revealing and had big consequences for water use and water management. This is one of the easiest, but also turned out to be a really elegant study done by Stan Smith, where he was working on the eastern escarpment of the Sierra Nevada mountains here in the western parts in California, is principally in Nevada. And Stan characterized the hydrogen isotope composition of his surface waters. This is the stuff that's running down the streams coming off the east side of the Sierra Nevada mountains. He went out there, he had a series of wells around his study site, and he also measured then the isotope variation in groundwater. He went, hallelujah, look at my groundwater, looks isotopically very different than my surface water. Cool, let's go out and see what the plants are doing. So then he sampled these poplar trees across the season here, and what you see is that early in the season when there's a lot of surface water runoff, they're using surface water, and as that surface water, remember this is basically a desert, it's the eastern side of the Sierra Nevada facing Nevada, so it is dry. And as these surface waters began to go away, abate, sometimes some of those streams just dried out, those trees went down and started using groundwater. So this was a really cool way that Stan was able to document without ever digging the plants up, using isotopes to basically say these plants are shifting. Their water sources, one type of the year they're using surface runoff, later in they're using a deeper groundwater source. This backfired against Stan for a few years because the California Water Resource Board, particularly the people in Los Angeles, got a hold of this and they said, oh, cool, we can divert the water coming off the Sierra Nevada because all the mature trees are just using groundwater anyway. Let's just take the surface water. We'll take it to Los Angeles, we'll use it. Why not? Look, the trees they'll just go use this. No big deal. Poor Stan. And he kind of was like, oh, shit. And he had to kind of push back against this. It took him a couple years, and then one of his PhD students, Dave Bush, they basically said, well, this is an incomplete story here. This is what the mature trees do, all right? But if we go out there and we start looking at the little trees that grow along these stream corridors, and if we were to divert that surface water, the little trees are definitely dependent on the surface water that's running off these streams every year. So if we divert all this water to Los Angeles and Las Vegas and other places to water all these golf courses, we're not going to have the next generation of riparian forest because we're going to kill all the young tree seedlings. So it ended up backfiring at first, but it led to a whole bunch of other studies that actually were really, really important for a water resource management issue in California. So the isotopes didn't lie, but they kind of came back and bit Stan for a few years until he was able to add some additional data. Here's a picture that you gave me, Darren. Here, this is where is this, Darren? Oh, good. Okay, let's go on. The Mojave, very good. That was in Mojave. When Darren was here, and Jim has been interested in this for a long, long time, of looking at the water resources that plants in desert environments use, and Jim and his group, Darren included, were really interested in some of these areas where different kinds of deserts come together. So the Mojave and the Sonoran, and they went to this place in southern Utah, which is a really diverse area full of a lot of different species of plants. And one of the things I think that vexed Jim for a long time is he says, why is it when we go to southern Utah and northern Arizona, when we start to get to this kind of mixture between the Mojave and the Sonoran Desert, that we get all this diversity of different vegetation types out there? How does a desert like that, a really dry desert, support all this diversity? And the hypothesis at that time was, well, maybe this diversity is partitioning up all the water resources out there. Maybe the different plant types are using different water resources. So they went out and they did a really nice study, very much like Stan's. They measured the variation in the isotopic composition of the summer rains, the winter rains, which are coming out of the northern part of the Gulf of Alaska, across California, and into southern Utah. So they're isotopically more negative. They're coming from colder regions and they're raining out than the monsoonal rains here, the summer rains. So you got a nice isotope separation, two really nice end members. And then they went out there and they measured the isotope composition of these different plants that are out there, annuals, different woody perennials, herbaceous plants, a succulent, probably a yucca, I imagine. Is that yucca? Yeah. And what you see is a really nice isotope separation. The annuals are obviously using these annual summer rains. Your herbaceous or your woody plants are using a wide range. So each one of these dots represents a different species. So you can see some use more winter precip, some use more summer precip. And they use this as evidence basically to explain that the plants, in fact, out in this area were maybe water partitioning, niche partitioning. And maybe that might be one of the reasons that leads to the greater diversity of plants being able to live in an otherwise water-limited environment. And it was a really nice example of how isotopes could come in a very elegant way and add an ecological layer to some of the things that Jim and Darren and other people have been curious about and working on for many, many years. But it's a very nice and very elegant application of how isotopes can come in and add a wrinkle that you're not going to be able to get with any other kind of data. You just can't get this any other way. And it was, I thought, a very nice and early application of the stable isotope method for plant ecological types of investigations. Those of you that went up to the meadow yesterday saw that system, and it was one that I worked on early on here, and it was a very curious one. Those of you who know a little bit about hydrology know that when we go to many different riparian systems, this is kind of the common thing that we see, what we call gaining reaches, where water falls into a watershed. That water percolates down into the groundwater system. That groundwater then basically feeds the stream system. So that's the common way that we normally think of water. When it falls onto the landscape, it refills the groundwater aquifer. The aquifer pretty much fills up what the stream is doing, right? And this is what we normally see. But those of you that saw the meadow up there yesterday, and here along the Wasatch Front, and actually many areas in the West here in North America, is we have areas that have either been cut off by landslides, they become perched in a particular way because of tectonic activity or whatever, and you can get areas where tributaries of streams are running down where they're actually a losing reach, where the stream is actually disconnected from the groundwater system, all right? And any water in the stream might eventually get lost to the groundwater system. And so Jim and I knew that we had these gaining and losing reaches here in the Wasatch Front, and we went up to the meadow where you guys saw this yesterday, and we said, hey, this might be a nice way for us to test where plants in riparian corridors along the Wasatch Front are getting their water. Are they using the stream? Are they using the groundwater? In different kinds of configurations of losing or gaining reaches, can we use isotopes to tell where the different vegetation is actually getting its water from? And we got some pretty interesting results. Here's now I'll plot these data in a different way here. Here's the hydrogen isotope composition of the plant, so what we extracted out of the plant, as a function of the size of the plant. All right, so here's our little guys, small trees down here, larger trees as we go to this side of the x-axis. And one of the things that you see, the small plants use a wide range of either soil water. So if you're really a small plant, some of you might use soil water, and some of you might actually use stream water. But here's the weird result. As we got to the larger plants, so as soon as we get to plants that kind of are around this area here, all these plants had hydrogen isotope values that didn't match any of the water sources that we measured out there. We measured the soil, we measured the stream, and went, oh shoot, are we boneheads or what? You know, what's happening? Jim said, God, this guy's a bad postdoc. You are fired. You know? And I said, well, wait a minute. So then we started talking to Kip Solomon. And Kip Solomon said, well, wait a minute. There's some really interesting geology and tectonic activity here in the Wasatch Front. And he said, let me go up to the meadow with you. And in addition to that, I said, well, we only measured hydrogen isotopes. Let's also get the oxygen isotopes and put them in that meteorological, the dual isotope space that we were looking at earlier in the lecture. So we went in and we wanted to look at whether or not we had our local meteoric water line, we had our stream water, we had soil evaporated water. So we wanted to kind of better constrain our isotope universe out there by having both isotopes. So we got the oxygen in addition to the hydrogen, And then we replotted the data after this paper was published. And so here's our local meteoric water line. These are the precip values. That's how you build your local meteoric water line, right? Here was what our stream water looked like. We went and looked at the soil water value. So there's that evaporation line. So that's nice. That fits what our expectations are. And we looked at some small trees. The surface soils are the gray. The small trees are the green. So pretty straightforward. Small trees are using surface soil water. And then we plotted our mature trees on there like we saw in the last plot. And they plotted on the meteoric water line, but they plotted off of any source that we had actually measured. And what we ended up doing is when we went up there with Kip, we put in a well and we asked, what water source are these trees using? They were using groundwater, right? We hadn't measured that initially. This is a losing reach. So the groundwater is getting from most of its isotope values from high elevation that's coming in this way. It's not getting it from the surface runoff. So there's two isotope worlds there. And we discovered that stream-side trees weren't using stream water. You know? Who would have guessed? Right? It's flowing over their roots, and you're thinking, okay, this is kind of crazy. And in also talking to Kip, who knows the geology here of the Wasatch Front, he said, well, that's not so weird to me. You know, it's so funny when you talk to people who know more about the environment that you do. He goes, yeah, that's no big deal. And I said, why isn't that a big deal? And he said, oh, because these streams dry out about every 5 years. He goes, so of course your big trees are going to park themselves on groundwater. That's the most permanent water source in the watershed. Because if the stream dries out, would you use water in the stream if it runs out? Of course you wouldn't. So, you know, when you start talking to people who know more than you do, I went in there very naively thinking that the plants were going to tell us that we're using stream water, and learned later on that they were actually using groundwater. But it was a very nice demonstration of how isotopes could come to the rescue. And as long as you characterize where all your water sources were, you could actually tell something about how to use that isotope variation to source where your plants might actually getting their water from. And in this case, it came from a very unusual place, something that we didn't expect, not in the groundwater and not in the stream water.
Does this sourcing idea work for use the same idea for bodies of water instead of plants? So if you're taking out your rainwater, your groundwater, isotope it, and then like take the stream water, you could trace where it's from.
It can work, yes, indeed. Yeah, there's a little bit more of a complication when you have surface waters. Many times they can go through evaporative enrichment. So they don't necessarily reflect exactly what the precip inputs were. There's been a post-precip modification. But as long as you measure that surface water and its isotope variation, you can do exactly the same kind of thing here. You just have to characterize it well. Surface water get exposed to evaporation. But yeah, it definitely can be used. Okay, I'm always running out of time here. I only have 15 minutes left. There's kind of a couple points I want to make here near the end. And I can't lead you through all the data, but I'll show you a couple panels of data, and I'll just give you the punchline. I mentioned the critical zone observatories that are being established here in the United States and actually getting established in Australia, and there's a couple now being established also in Mexico. And what they're really interested in is sort of linking what's going on from the weathered bedrock zone here all the way through the water table into the fractured bedrock, the saprolite, and the soil through the vegetation and into the atmosphere. They're so really trying to understand that zone where life is on our planet, from the rock to the atmosphere. And a lot of the work that's being done is trying to characterize what is happening in the below ground environment. And as we started to do this work, we have gotten a whole bunch of new isotope surprises, all right? And mostly just because, and you would think this wouldn't be true, but we haven't really been making very good measurements in the below ground environment. We go down a couple of meters, and it's mostly because that's easy to do, right? But when you really start digging into the subsurface and you start interrogating what's going on in this area here where there's fractured bedrock, and this occurs in everywhere on the planet, there have been some really interesting isotope surprises going on in that below ground environment. And I'm going to see if I can just go to one of the plots. No, I'm going to go past this. and go to, let's go to this. Go forward in your slides to this slide here. It's on page 32 at the bottom, all right? When we start characterizing the water in the subsurface, we start characterizing the water in the soil, the saprolite. You guys know what the saprolite is? That's not the soil, but it's not the rock. It's the stuff in between. It's a mixture of larger stones and things that have, basically, you know, as the earth moves up and it basically creates our hills, all right, what's happening is getting fractured, then you start to get finer and finer particles. You don't have any organic matter in the saprolite. It's still all geological materials, but there's a mixture of fines and coarse materials, but you don't have any organic inputs yet. And then you finally get to the soil where you develop your soil horizons because of your organic inputs and the development of the soil horizons. But the saprolite in many environments can be a very, very thick area that lots of water can go into, all right? And that actually sits above the fractured bedrock, which also can have a giant reservoir. That's where our aquifers sit, in the fractured bedrock, all right? So what people have been measuring now is looking at what the isotope composition is of the rock, all right, here, the saprolite, the soil, and we're starting to get things that show weird isotope excursions from what the meteoric water line suggests should be happening out there. If we're measuring everything that's coming in, it should sit somewhere either on the meteoric water line or on that evaporated side that we talked about before. But look at these data. Look at where they're sitting. They're sitting in an isotope universe over here that we don't know about, right? Spock, phone home, right? It's like, we're out in an isotope world here that we don't understand. And the cool thing is that lots and lots of people are measuring this. They are starting to see these isotope excursions in directions that we've never seen before. And what it's done is it's raised the question, hey, wait a minute. When we get into the subsurface, where we have all these exchange surfaces, geological exchange surfaces, clay mineral surfaces, mudstones, sandstones, areas where there's different elements, magnesium, calcium, sodium, etc., that can take up water, hang on to water differentially, let some of it flow through. Do we see isotope effects? And you bet we do. And we're starting to really show now that there are some subsurface fractionations that are associated with the chemical and the material properties in the subsurface, in the lithosphere, which covers our planet, so we can't ignore it, right? And we're really working hard now, along with some of the other CZOs, to try to explain the underlying mechanisms behind why we see these isotope excursions into an isotope space that we don't measure in the precip. These are post-precip modifications that are happening because of material and chemical properties under our feet. And they're being shown over and over and over again. And there's some fractionation processes that are associated with them. Some may have to do with the chemistry, the alkalinity in particular, in the subsurface. Some may have to do with, as I just mentioned, whether those surfaces, like the charged surfaces in the below ground, hang on to the lighter isotopes more easily than the heavier isotopes, all right? Or vice versa. I can't give you the full punchline here, but what I can tell you is that now that we're starting to get unlazy and not go down as far as we can only dig with a shovel, but get in there with drilling rigs and characterizing the below ground environment, we're starting to see that actually that below ground environment represents massive water storage. We, working in the Coast Range of California now, this is Danielle Rampey's work, she basically characterizes that the coastal range of California, from San Francisco Bay north, contains as much water as the aquifer lying under the Great Central Valley of California. It is literally hundreds of billions of gallons of water that's in the hillside, and it's in the fractured rock. And it's a water resource that we've never really thought about. It's isotopically weird because it stays in the rock. It goes in there. We've tritium dated it. Some of it's 5,000. Some of it's 25,000 years old. All right? So there's a bunch of stuff going on in the subsurface here with respect to water resources that we've never really appreciated. And it's throwing some isotope curveballs at us. Because some of the plants in California, for example, they're rooted into this. And it was kind of like the story I told you from Red Butte Canyon. Until we started digging into it, we didn't have any idea what the isotope value of that water source actually was. And yet we have trees that are reflecting it. So they're clearly tapped into it and using it. And if we just measured the surface properties, it was a source we didn't actually measure. So, you know, I'm happy to talk with any of you that are really interested in this because we're running out of time. But just beware that some of this work now in this critical zone is really revealing some very unique opportunities to characterize hydrologically and ecologically what's going on in the subsurface and how that water resource may feed certain vegetation types, may feed certain groundwater systems, may be isolated from those systems. And yet there's huge amounts of water in those hill slopes that we haven't done a very good job of characterizing and including in the hydrologic cycle. They're out of mind. We haven't seen them because we haven't really tapped them before. So we're spending a bunch of time and a bunch of resources, like a bunch of our colleagues that are working in the CZO, to actually understand more about what's going on in the subsurface. And some of this comes out of a thesis that's been done by a guy named Jasper Ocean at Berkeley. One of the PIs on the Shale Hills Critical Zone Observatory, Sue Brantley, Cliff Reeby, who's at University of Wyoming. There's a bunch of us kind of nibbling around the edges and coming at this from various locations, and I'm totally charged up about it. Because, boy, when you get a new isotope value and that you can't get any other way, you just kind of go, oh, send me in, boss, I want to go. You know, and you want to just dive into the subsurface because you can see that there's something really interesting going on that we have not ever thought about before. Yes?
So, lower valley for those weird ones, right?
Yeah.
Did you say, does that represent water time past?
Yep.
That's glacial. That's when California was colder, and therefore isotopic values are like this level.
Absolutely. So we tritium dated these black values here. They tritium date to 12,000 years ago. Right. So we're looking at Pleistocene water. All right? And this is not, the weird thing is, there is a literature out there that has shown this before. You go to the UK, and people ask, what's the water in the White Hills of Dover, right? The famous White Hills that we all seen in movies. And they measured the water in there, and they also tritium date it, and they see that it's glacial water. It came from the time when there was glaciers on England. And this is the same sort of thing here. So we're seeing that there's probably very old water that we've been ignoring. And some of it is isolated. It's actually not part of the hydrologic system right now. And we're wondering, as California dries out, which it's doing, and the trees have to go find their water somewhere else, whether we're going to start seeing them tapping and transpiring really old water, you know, because that's the only water out there, right?
So you'll have selection on trees for deeper roots.
For deeper roots. Yep, exactly right. Or plants that don't transpire very much.